All right, everyone, welcome back. All right, so let's see here. Today is Wednesday, October 28th. So one more session before the election, I guess, right? Okay, so today is October 28th, Wednesday. All right, we're going to do lesson 26, 27, and I'm going to do a good bit of starting lesson 28, which I'll continue with next time. So I'll kind of blend that lesson. So I am going to start lesson 28 substantially today, actually. All right. On part 4 of the class, lessons 24 through 32 will be due just before the Thanksgiving break. So it would be the Thursday before the Thanksgiving break, 1 week before Thanksgiving, on November 19th. All right, so any questions before we start? Okay, feel free to chat. I think I should have time for some fun videos at the end, like the links I sent out. Any questions before we start? Yeah, good question. So yeah, that's something I'll be working on over the next week and a half or so. I have a number of homeworks to grade. Yeah, I can't make a prediction, but obviously that's next for this class. So I'd say within, I can't give a precise timeline actually. Okay, suffice to say that as soon as I can get to it, I'll get to it. All right, probably well before the Thanksgiving break. That's the hope. Well before the Thanksgiving break. Yeah. Okay. All right. Any questions before we go on? Any other questions? All right. I can never predict the schedule. There's always something coming up in terms of the schedule of grading. Right. This schedule is very set, though. All right. So let's go ahead and start then. All right. Questions in chat. All right.
Hi, everyone. In lesson 26, we're going to talk about a variety of distributions that we're going to help us construct confidence intervals next week. Now, we've already met the standard normal Z distribution, and we're going to talk about other distributions, the T distribution, and the T distributions, plural, and the chi-squared distributions, plural. But there is only one standard normal Z distribution. I should have said the standard normal Z distribution, although it inspired us to generalize this to other normal distributions. But we're going to compare and contrast the Z distribution with the T and chi-square distributions that we'll discuss later on. So let's review the standard normal Z distribution. All right, so this is the normal distribution. We're reminded of this bell-shaped density curve. This distribution has mean 0, no units, mean 0, and standard deviation 1 unit. And what were some properties, some other properties of the standard normal distribution, what I call the Z distribution? Well, they're continuous. In fact, all of these distributions will be continuous. The Z, the T's, and the chi-squared, they will all be continuous. So we're going to have density curves for all of these. A normal random variable, including the Z, can take on any real number as a value. The density curve is bell-shaped, as the T's will be. The total area under the density curve and above the Z-axis is 1. Well, that's true for any probability density curve. The area between the curve and the horizontal axis will always be 1, because 1 is always total probability. Remember, the 1 up here corresponds to the standard deviation being 1. The 1 here means that the area under the curve is 1. They're different ideas. Again, the mean of the Z distribution is 0. The center is 0. The density curve is symmetric about the mean. So we have mirror images to the right and to the left. And the standard deviation is 1. Again, visually, the standard deviation, I'll try to do this better. So the mean is 0. The standard deviation is 1. And although you don't really have to know this for this class, it's nice to know this for drawing good pictures. But the standard deviation is the distance between the mean line, the 0 here, and by the way, mu is 0, the mean. Sigma, the standard deviation, is 1. We use population parameter notation for distribution parameters. The distance between the mean line and either inflection point, that's the standard deviation. This normal bell curve has 2 inflection points, one over here and one over here. They're symmetric about the mean line. You learn about inflection points in calculus. These points are where the graph changes concavity, kind of like curvature, from concave down to concave up, or vice versa. The picture down here may be more helpful. This is from Mathematica. So here is the z distribution. Here's the probability density curve for the standard normal z distribution. The mean line is at 0. Again, no units. The standard deviation is 1 unit. No particular unit like feet or miles. These are 2 inflection points. Again, the standard deviation is the distance between the mean line and either inflection point. Again, that's nice to draw good pictures, but you don't have to know that. More generally, for a general normal distribution, the mean does not have to be at 0. The standard deviation does not have to be 1, although it does have to be positive. But those are for general normal distributions. The z is the star of the show. The key normal distribution we're going to deal with is the z distribution, the standard normal. So that was a review of the standard normal z distribution. We're going to explain and discuss similarities and differences between the z distribution, the t distributions, and the chi-square distributions later on.
Okay, so any questions about that review of the z standard normal distribution? That's a review. Any questions? Because we're going to deal with the similar t's next. All right.
Hi, everyone. So we reviewed the standard normal, or z distribution. Z-scores are used more generally, but when we talk about the z distribution, we're referring to the standard normal. Now, we're going to talk now about the t distributions, plural, because there are many of these, infinitely many of these. The t distributions are also called students' t distributions. Actually, there's a good history to the t distributions. Basically, they were invented and studied by a worker at a brewery in Ireland. And because of the rules at the brewery, he had to publish under the pseudonym student. So this comes from the work of a brewery worker, although hopefully not while he was drunk. Anyway, these t distributions are similar to the standard normal z. For example, these t distributions are all bell-shaped, but notice I'm drawing these a bit differently. Well, like the z distribution, they're continuous. So we have this continuous density curve. We're not talking about bars like for a binomial. A t random variable can take on any real number. The density curve is bell-shaped. The total area under the curve is 1. So far, it's basically like the z. The mean is 0, again, like for the z distribution. And again, we have symmetry. So all of these characteristics for the t distributions are the same as for the z distribution. Nothing is different so far. But now, and also this too. I could add this too. The tails fall off rapidly. I guess I listed the similarities first. These are all similarities. Right? The tails of the curve fall off rapidly. Okay, which means that you cannot have too much too far out. You're not going to have too much further than 3 or 4 standard deviations away from the mean. So these are all similarities between the t distributions and the z. But what are some differences? Well, as I said, there's only one z distribution. Yes, it can be applied to infinitely many normal distributions, but there's only one standard normal z distribution. But there are infinitely many t distributions. We don't have a standard t distribution, although we do have a generic bell shape. Now, that's one reason why whenever I talked about bell curves before, I was a little nervous because there are different kinds of bell curves. They're not all normal, like the standard normal. The t distributions also had bell-shaped density curves. So not all bell curves imply normal distributions. Okay, here we have t distributions, and we have infinitely many of them. Now, back with the z distribution, the standard deviation was 1 unit. For a t distribution, the mean is 0, but the standard deviation sigma is greater than 1. And the tails, by the way, although they do fall off rapidly, they don't fall off as rapidly as for the z. So for example, for a t distribution, you're going to have more stuff, more probability mass, more than 2 standard deviations away from the mean, more so than for the standard normal z. So in a way, this represents greater uncertainty. There's greater variability out here in the tails. I should put arrows out here. The tails are thicker. The tails are thicker. Things are more spread out, representing greater overall uncertainty. Now, again, there are infinitely many t distributions, and they're indexed by the number of degrees of freedom. So we have a t distribution on 1 degree of freedom, 2 degrees of freedom, 3 degrees of freedom, and so forth. If you give me a positive integer n, there's a t distribution with that number of degrees of freedom, or df. There's a t distribution on 1,000,000 degrees of freedom. And by the way, that kind of a distribution will really resemble a z. If the number of degrees of freedom, if the number of df is large, then a t distribution can be closely approximated by a z distribution. I'll discuss that in a moment. But anyway, we have infinitely many t distributions corresponding to 1 degree of freedom, 2 degrees of freedom, and so forth. So in tables, you see rows for 1 degree of freedom, 2 degrees of freedom, and so forth. Again, this number of df can be any positive integer. And for most basic applications, like what we see in our class, if n is the sample size, like the number of people in a poll, then we want to use the t distribution on n-1 degrees of freedom. Actually, the t distribution is used more for small sample sizes. For a poll, n tends to be rather large, and we could probably use a z anyway. But if n is fairly small, then we're really going to want to use the t distribution on n-1 degrees of freedom. So for example, if the sample size is 10, then we want the t distribution on 9 degrees of freedom. Again, if n is 10, if the sample size is 10, then we're talking about the t distribution on 9 degrees of freedom on our basic applications. Remember that student, his real name was William Gossett. Gossett was a researcher for a brewery company. So I guess they cared about just a small number of beers. Who knows, maybe he drank them afterwards. I don't know. But Gossett dealt with small samples at the brewery. Again, as the number of df increases, a t distribution looks more and more like a z distribution. And by the time you get to high numbers of degrees of freedom, like in the hundreds, like for a poll sample size, then for all practical purposes, you can use a z. The t distributions, their tails get thinner and thinner. Remember, the z had very thin tails. The z distribution has very thin tails out here. You have very little probability mass, several standard deviations from the mean. And the standard deviation started off as greater than 1. Okay, for a t distribution, the standard deviation is greater than 1, but as the number of df approaches infinity, as it gets larger and larger, then it approaches 1. The standard deviation approaches 1. So the standard deviation decreases. In a way, we're saying that uncertainty decreases and the standard deviation approaches 1, which is the standard dev for the z distribution. Again, if the number of df is large, like in the hundreds, we often approximate a t distribution with a z because there's not much of a difference anyway. We can illustrate this using pictures. I used Mathematica to graph these out. So in the figure below, all right, in orange, this orange dash curve, that's the density curve for a t distribution on 1 degree of freedom. Okay, that's this shorter distribution with thicker tails. It's more squat. The blue dotted curve is the t distribution on 5 degrees of freedom. You can see that its peak is higher up here, and its tails are thinner than the orange tails for the 1 df t distribution. And the idea is that as the number of df, degrees of freedom, gets larger and approaches infinity, the peak gets higher and higher and approaches the peak of the at the z distribution, the peak for the z distribution, and the tails get thinner and thinner. Again, for 1 degree of freedom, the tail here was a bit thick over here and over here. Bear in mind, the t distributions are also symmetric. They're all symmetric about the mean line at 0. And the idea is that we're going from the orange distribution, the t distribution on 1 degree of freedom, to the t distribution on 5 degrees of freedom, up towards this z distribution over here. So it's getting taller near the mean, and it's getting thinner near the tails. And the standard deviation is getting smaller and smaller. We're getting more and more bunched up around the mean line of 0 as we go from the orange curve to the blue to the black. If we're talking about hundreds of degrees of freedom, then the t curve is very, very close to the z curve, and we may as well use the information for the z distribution. Like our information from software or tables, we may as well use z information. All right, we've talked about the z distribution and the infinitely many t distributions, which had different numbers of degrees of freedom. Next, we're going to talk about the chi-squared distributions, which look a fair bit different. They are a fair bit different. Next time.
All right, any questions? So the t density curves are bell curves. Okay, and in fact, they start approaching the z curve as the number of degrees of freedom approaches infinity. The chi-square guys look very different. Any questions? Any questions? All right.
Hi, everyone. We're finishing lesson 26 with discussing the chi-square distributions. These distributions will be used to find confidence intervals for standard deviation and variance later on. For confidence intervals, for standard deviation, and variance. And there's a key feature of these chi-square distributions which will be related to these parameters. So that's the Greek letter chi. If you go on a college campus, well, not now, but if you go on a college campus maybe a year or two from now, then you may recognize this Greek letter chi on, say, a fraternity. Chi-square distributions. And these guys have, again, both similarities and differences compared to the z and t distributions. So, for example, what are some similarities that these chi-square distributions have with the z distribution, let's say? And again, the t distributions look a lot like this guy. All right, well, the chi-square distributions are continuous. I'll tell you right now that a more generic chi-square distribution looks like this. Okay, it looks a little bit stranger. And yes, there is a brick wall at 0. We'll get to that. Okay, but both chi-square distributions and z and t distributions are continuous. We have this density curve here, right? The total area under the curve is 1. That corresponds to total probability. And like for the t distributions, there are infinitely many chi-square distributions indexed by the number of degrees of freedom. or DF. So in that sense, they're like the T's. But there are also differences. Before we get to the differences, let's talk more about degrees of freedom, right? Again, different chi-square distributions corresponding to different numbers of degrees of freedom. The number of DF can be any positive integer, 1, 2, 3, and so forth. Again, like for the T's, for most basic applications, if n is the sample size, then we typically want to use the chi-square distribution on n-1 degrees of freedom. So for example, if the sample size n is 10, then we want to use the chi-square distribution on 9 degrees of freedom. Okay, just like for a T distribution. And the Z distribution did not have any degrees of freedom. So far, I've been talking about some similarities between.
But I think I meant DF equals 9. If the sample size n is 10, the number of degrees of freedom, DF is 9.
In the chi-square distribution, distributions, and the T distributions. And like for the T distributions, as the number of degrees of freedom increases, a chi-square distribution will look more like a normal distribution. Now, the T distributions look more and more like the Z distribution, the standard normal distribution, as the number of DF approaches infinity. But the chi-square distributions, as the number of DF approaches infinity, approaches a normal distribution in general, but not a standard normal. It does approach a normal distribution. The curve looks more and more bell-shaped, but it won't be a standard normal. The mean will not be 0. In fact, in general, the number of degrees of freedom will be the mean for the chi-square distribution, and it's never 0. There's no such thing as a chi-square on 0 degrees of freedom. Right. And again, if the number of degrees of freedom is large, we might approximate a chi-square distribution by a normal distribution, although that's less frequent. It's more often that we approximate a T distribution by a Z distribution if the number of DF is huge. Okay, let's discuss some differences now between the chi-square distributions and the Z and the T's. The brick wall I was talking about. When you look at a chi-square distribution and you draw a density curve, there is a brick wall at 0. A chi-square random variable can only take on non-negative real numbers as values. The value of a chi-square random variable cannot be negative. Of course, that was not true for Z or T. For example, up here, let's look way back at the standard normal Z distribution. Of course, you could get negative values for Z, like negative Z scores. T scores can be negative also. T scores can be negative also. But chi-square values cannot be negative. Well, chi-square can never be negative in value, and you can probably tell that the mean cannot be 0. I mean, look at this thing. There's no way that the mean is at 0. We pretty much have to have negative values in addition to these positive values. We would need negative values to be legal pretty much. So the mean is not 0. And again, you won't have to really know this, but the mean of a chi-square distribution equals the number of degrees of freedom. Remember that the mean was 0 for the Z and for the T's. Also, we lose a key property. We lose symmetry about the mean. The Z and the T's, they were all symmetric about the mean. So see here, the Z curve in black, the T curves in orange and blue, they're all symmetric about the mean line at 0. Chi-square distributions, they're not symmetric, they're asymmetric. So we lose some key properties. That's one reason, for example, why, remember how I mentioned before, we're going to use these distributions to do CIs, confidence intervals, for standard deviations and variances. These CIs will not be symmetric about their mean. And in part, that's because of the asymmetry of the chi-square distributions. Also, what else is true about standard deviations and variances? They're never what? In value. They're never negative. And that's also related to the fact that chi-square values are never negative. We have nothing over here. So what do some of these look like? Actually, the chi-square density curves on 1 and 2 degrees of freedom, they look a bit different. They look like slides. So in red, here's the chi-square density curve on 1 degree of freedom. And in blue, here's a chi-square density curve on 2 degrees of freedom. These are like slides. They're a bit unusual because other chi-square curves have a peak that's not on the y-axis. They have a peak that's a bit over to the right. So for example, in orange, here's the curve for a chi-square distribution on 3 degrees of freedom. Again, you cannot take on negative values. These guys are out. And the curve peaks a bit to the right of 0. Then it falls off. In blue, this dotted blue curve, that's for the chi distribution on 5 degrees of freedom.
Chi-square.
And in gray, you see the chi-square distribution on 10 degrees of freedom. You may be able to see that as the number of degrees of freedom increases, we're approaching more of a normal bell shape. But the mean cannot be at 0. In fact, the mean for a chi-square distribution is always at the number of degrees of freedom. So for example, if you have a chi-square distribution on 1,000 degrees of freedom, then the density curve will look almost normal bell-shaped. It'll look very close, and the mean will be 1,000, the number of degrees of freedom. So again, the chi-square distributions look a lot different from the z and the t's, and we're going to use these to develop confidence intervals for standard deviation and variance. Okay, so what values from these distributions are we going to use to construct our confidence intervals? They're called critical values. And that's going to be the topic of lesson 27.
So remember, last time on Monday, we were talking about confidence intervals. We're going to talk about how to develop them, right? How do you actually get the lower and upper limits? We're leading up to that. Questions? Questions. Again, feel free to put questions in chat. All right.
Hi, everyone. We're on lesson 27 on critical values. These are the numbers that tell us how the confidence levels, like 95%, affect a confidence interval. The critical values, or CVs, as I'll abbreviate them, come from distributions such as the z, a t, or a chi-square distribution. And in lesson 27, we're going to be working a lot with notation. So you're going to learn to be familiar with various notations like these. So we're going to use 2 critical values, or CVs, to construct a 1 minus alpha confidence interval, or CI, for a population parameter such as a mean mu, a population mean mu. Now remember, what makes a confidence interval a confidence interval? Well, an interval estimate is a range of values, like your TA saying, I think that the mean test score in the lecture class is somewhere between 70 points and 78 points. And if you ask your TA, Igor, how confident, how sure he is that the mean will be between 70 points and 78 points, and if Igor says, oh, I'm 95% sure, or 95% confident based on my statistics, then, well, based on statistics, hopefully it's not too personal, but based on Igor's knowledge of statistics, there's a 95% chance that the true population mean is somewhere between 70 points and 78 points. So if you attach a confidence level, like 95%, 95% is standard, although we will use different ones as well in this class. If 95% is the attached confidence level, all right, then we have a 95% confidence interval. So 1 minus alpha would then be the decimal equivalent, 0.95. So 1 minus alpha is the confidence level in decimal form. And the standard confidence level is 0.95 in decimal form. All right. Now, if we're using a z distribution, then we denote, I'll move this up, then we denote these critical values, which again are the key numbers from the distribution, like z, that we're going to use to construct these confidence intervals. These critical values are going to be denoted by plus or minus z sub alpha over 2, or half alpha. Wow, why is that? A picture would help. And bear in mind, you don't have to worry so much about this notation on homework or exams. Well, you'll see it. I mean, you will see this in formulas. I want to explain why this notation looks the way it does. And by the way, we will see similar notations for t-distributions, but for chi-square distributions, remember, chi-square values are never negative, so we're not going to have the plus-minus symbol for chi-square critical values. Anyway, let's explain this notation. Why do we denote the critical values from a z-distribution as plus or minus z sub, meaning subscript, alpha over 2, or half alpha? All right. It comes down to this picture. All right. So we have two critical values. Let me extend the window a bit. All right. So we have two critical values from the z distribution that we're going to use to develop our confidence interval for mu, a population mean. Okay. So we have two critical values, z sub alpha over 2, which is going to be a positive value, and its opposite over here. These are going to be the two critical values, and as you might suspect, they're going to be symmetric about 0, the mean of the z distribution. Because remember, the sample mean is going to be at the center of our confidence interval, and this is a reflection of that symmetry. Okay. Now, once again, we're looking for a certain confidence level. Let's say 0.95, our standard, right? So if 0.95 is our confidence level in decimal form, 1 minus alpha, our confidence level, is 0.95. Well, then what's the complement? The complement of 1 minus alpha is just alpha. These are complementary probabilities because they add up to 1. Now you might be wondering, why are we labeling the confidence level this 1 minus alpha jazz? Because alpha here, which is going to be the total tail probability, the alpha here is going to have literally significance in the last part of our class. In fact, alpha is going to be called the significance level in a hypothesis test. Anyway, if 0.95 is the confidence level, if that's 1 minus alpha, then what's the complement? What's the value for alpha? 0.95 plus what will get us 1? 0.05. In other words, if we have 95% in this white region in the middle, we're going to have 5% in this, we're going to have 5% total in the two blue regions in the tails. All right. Now you see here two tails. This total tail probability of alpha is going to be split in two. And that's why we have half alpha, or alpha over 2, over here, representing this area or probability in here, in this left blue region. And the same by symmetry, half alpha, or alpha over 2, which represents the area in blue in this right tail over here. We have symmetry between the two tails, corresponding to the fact that we have symmetry between these two critical values. Now later on, when we use t-distributions, we're going to use a similar notation, except that instead of z's, we're going to use t's. But it's going to be really the exact same picture, except that we're going to replace z's with t's. The chi-square pictures, however, will be different, okay? Because the curves there look different and there's a brick wall at 0. And we'll discuss those later on. Okay. So what if we have a 95% confidence level? then you might be able to memorize these. Many stat students actually do. What are the critical values that correspond to a 95% confidence level or confidence interval when a z distribution is involved? So what are these critical values that will trap 95% or 0.95 probability mass in the middle and a total of 5%, 0.05, symmetrically in the two tails? Remember, it's 5% or 0.05 total in the two tails. For each individual tail probability, you cut in half. So it's 2.5% or 0.025 in the left tail and 0.025 in the right tail. Okay. Now, if you remember the empirical rule, and I hope you do, the 68, 95, 99.7% empirical rule, we expect that with really approximately normal data, that about 95% will lie within 2 standard deviations of the mean. So a clever student with a good memory might think, hey, the critical value here should be about +2, and the critical value here would be about -2. And that student would do a very good job. However, we can refine the estimate a bit more because this rule was not super accurate. Instead of 2 and -2, to 2 decimal places, we should use +1.96 as our positive critical value. So this thing here, the 1.96, is our z sub alpha over 2 critical value. And its opposite, -1.96, will be the opposite of z sub alpha over 2. So these are the 2 critical values if you're drawing from a z distribution, and if you're looking for a 95% confidence level for your 95% confidence interval. Okay, what about 90%, which is also one of the more common confidence levels? For a 90% confidence level for a z distribution, again, some students memorize these critical values. Here the critical values will be about ±1.645. +1.645 and -1.645. It makes sense these are a bit closer to 0 because we're trapping less probability, only 90% or 0.90 in the middle. Remember, for 95%, when we were trapping 95% in this white space in the middle, the CVs were out at + and -2 almost, really about ±1.96. If we're trapping less probability in this white space in the middle, then these values would be closer to 0. They're more closed in, about ±1.645. And by the way, we often go to 3 decimal places because, in fact, it really is almost smack dab in between ±1.64 and 1.65. So to 3 decimal places is pretty accurate. All right, so these are the critical values that trap 90% or 0.90 in the middle. That means we have alpha or 10% total remaining for the 2 tails. And we always split the tail probability symmetrically between these 2 tails. Even for a chi-square, we're going to do that. So the 10% gets split up into 5% for the left tail, 5% for the right tail, symmetrically. And again, that corresponds to the fact that the CVs are opposites. All right. For a 99% confidence level, now as opposed to 95%, we're really going to spread the CVs out. We're going to trap a lot of white space in the middle. We go outward. We go outward to, look at this, +2.58 and -2.58. And these CVs will trap 99% or 0.99 in the middle. 99% in the middle, so that means 1% total in the 2 tails. That leaves a measly 0.5%, 0.005 in this tiny left tail over here and in this tiny right tail over here. Again, we use symmetry. We're breaking this in half, each half for each of these 2 tails. Now, stat students are not required to memorize these critical values, but as you do your homework, you tend to see these values a lot. Because if I give you a confidence level, and if you know you're dealing with a z-distribution, then there are two particular critical values you're going to deal with. And for the common confidence levels, like 95%, 90%, and 99%, which are the three most common confidence levels, many experienced stat students actually remember these critical values for a z-distribution. Later on, I'll show you how we can deal with critical values for t-distributions and chi-square distributions, but you're not as likely to remember those critical values. Why not? Because how many t-distributions and chi-square distributions are there? There are infinitely many t-distributions and infinitely many chi-square distributions. It would be a total waste of time to even try to memorize the special critical values in those cases, even for these special confidence levels. There's just too many values. At least for the z, for the single sole solitary standard normal z distribution, well, over time, you tend to memorize these things. Especially since, for example, for 95%, you have about plus or minus 2 here. These are pretty easy to remember. All right. Next up, we're going to talk about, well, how to use software to find critical values, and how we actually construct confidence intervals. And we may as well start with software. We can look at things like Excel, for example, next time.
Any questions so far? I've examined here critical values for a z-distribution, the z-distribution, and the three popular confidence levels. Questions. These are numbers you see a lot of. Questions. I think we're doing software next.
Hi, everyone. As a bonus to lesson 27, I hope you're curious. Well, how do we get these critical values? How can we use online software to help figure these things out? Let's say you want to do your own statistics. Let's say you want an 80% confidence interval. All right, so let's see how you can find these critical values for a z-distribution given this confidence level of 95%. We're going to see how we can get the plus or minus 1.96. All right. Well, the easiest place to go to would be tutorhomework.com because there's this middle operation here. So notice here that we're looking at these two z-scores that are trapping 95% or 0.95 in the middle. So this website is very well suited to finding those kinds of values.
By the way, I think I have the, yeah, I'll send you the URL here. I've given it to you before. I'll put it in chat. Okay, so you can play with it right now, in fact.
We want to trap a probability of 95% or 0.95 in the middle. So I'll put 0.95 in the probability box here. I'll click on this arrow, and you see we get a z-score of 1.96 corresponding to the positive z-score over here. And by symmetry, you can figure out that the corresponding negative z-score is negative 1.96. But let's say that we go to a brute force table. Back in the olden days, we might have to use a table. Or maybe all you have is a textbook. Take out that z-table. Okay, so actually the negative z-score is easier to find because remember, we're trying to get half of 5% or 2.5%, 0.025 to the left of the negative z-score over here, this negative critical value. So we're looking for a z-score that corresponds to 0.025 probability or area to the left. It's like the 2.5 percentile kind of the z-distribution. Okay, well, remember for a z-table, you look for probabilities inside the body of the z-table. So we look for 0.05 in the body here.
0.025.
We know it's going to be a negative z-score.
I should have said 0.025, right?
Because we're going to be over here to the left of 0. We want to trap 0.025 in here, in the left tail. And these give cumulative probabilities, meaning left tail probabilities. Kind of like how many Netflix videos have you watched cumulatively from day one of the lockdown till now? You might say 1,000 videos cumulatively. All right, so where's the 0.025 in here? 0.025 in here. Ah, it's right here, 0.0250. We look inside out, negative 1.96. That should be a very good approximation. Gotta move this down a bit. Okay, so negative 1.96. All right. On the Rossmann-Chance applet, by the way, you can get this in the upper right, in the applet collection under probability, normal probability calculator. I'll erase this here. In Zoom, you have to erase the annotations. Okay, so I want a z-score with the property that I have 0.025 cumulatively to the left. All right, click outside. It's going to be a very negative z-score. In fact, to find out more decimal places, I got to click in here and move my cursor. Negative 1.960 to 3 decimal places. It's negative 1.960 to 3 decimal places. And by the way, for the positive critical value, you could do this. You could make it is greater than the 0.025, and you get the positive 1.96 value to get the right tail probability. Or if you want to find the positive critical value another way, here's another way you could do it. You could say, well, I need 0.025 to the left of this guy here. All right. I need 0.95 in the middle. So you add these. 0.025 plus 0.95 means that from this positive critical value, okay, how much do you want all to the left? You want a grand total of 0.95 plus this, or 0.975 to the left of the positive critical value. So in the Z table here, if you look at, if you look for 0.975, .975 here, 0.9750, you look outside, you get the positive 1.9, again, 6. In the Rossmann-Chance applet, okay, you want all the stuff to the left of, okay, some value, again, to the left of, to the left of what z-score do we get a probability or area in dark blue of 0.975? The answer is 1.96. It's almost 2. All right. And what about Excel? Well, we talked before about percentiles, right? What is the 85th percentile of the z distribution? That was about 1.04. I'll take you back to, how about the Rossmann-Chance applet. Let's go to the Rossmann-Chance applet. Okay, so.
Oh, no, this is a tutor homework, by the way. This is a tutor homework site. I think it's most user-friendly.
What was the 85th percentile of the z distribution? Put 0.85 under probability or area. Okay, the corresponding z-score was about 1.04. Or about 1.036. That's what Excel is spitting out, basically. So that's the 85th percentile of the z distribution. Again, what we're doing here is we're trying to find the kind of the 2.5 percentile. We want 2.5% to the left of this negative critical value. So equals norm.inv. We're going backwards from a probability to a z-score. What's the z-score that has 0.025 cumulatively to the left? It's a standard normal, mean 0, standard dev1. Well, hey, look at this. It's almost exactly negative 1.96. It's very close to negative 1.96. Okay. And then, of course, for 97.5% to the left, that's how you get this positive z-score. I hope you can use symmetry. You can figure out it's going to be positive 1.96, but you can figure out what's basically the 97.5 percentile. The standard normal is the positive version, about 1.96. So if you actually want to figure out what these critical values are going to be for the z distribution, for various confidence levels, you should be able to figure out using certainly tutor homework. That makes things very easy. But even from an old school table or the Rossmann chance applet, where you could go in either direction, left or right, pretty quickly, or using Excel. Next up, how do we use these critical values to construct confidence intervals? Next time.
Okay. And by the way, on the homework, I'll give you hints, right? But it's nice to know how I get those hints, right? How is it that I get these various values for the hints? Okay, so I've shown you ways of getting the critical values using software, online stuff. Now let's actually construct CIs. Questions? Questions. We're going to construct confidence intervals.
Hi, everyone. We're now actually going to construct these confidence intervals. So for example, remember our previous example with our TA Igor, who helped us grade a math test in a big lecture class. We asked Igor, so based on the 5 exams that you graded, can you give me a confidence interval for the true population mean for the class after all 1,000 tests are graded? And then Igor might say, Master, I am getting a confidence interval between 70 points and 78 points with 95% confidence. So this is a 95% confidence interval. So how do we actually construct something like this based on sample statistics? All right. In lesson 28, we're going to estimate, for example, provide point and interval estimates for a population mean mu in this unusual case where sigma, the standard deviation, the population standard deviation, is known. Now you might legitimately ask, well, if we don't know the population mean, how can we know the population standard deviation? That's a good question. And we'll address this kind of issue in just a moment. But for right now, let's just say that the theory and the procedure is more natural in these cases. In particular, we can use a z distribution to construct confidence intervals in this situation. Of course, the more common situation is where sigma is unknown. That's where you use t distributions, and that's going to be later on in lesson 29. Okay, so in lesson 28, we're going to estimate a population mean mu if sigma, the population standard deviation, is presumed known. And we're going to use the z distribution to construct confidence intervals for mu in this case. All right. So what are the assumptions here? In this lesson, we're going to find a confidence interval for mu, the population mean. And we describe these as 1 minus alpha confidence intervals. That's the typical notation. Because remember, 1 minus alpha corresponds to this region in the middle, this white region in the middle, the probability or area inside this white region over here, the area. And then alpha, the complement, is the total in the two tails. And often in actual tables or with software, you use alpha or half alpha to figure out what these critical values are. Anyway, we want to find 1 minus alpha confidence intervals for a population mean mu. What was the most common confidence level? The most common confidence level was 95%, or 0.95. But we also see 90% confidence intervals, 99% confidence intervals, 80% confidence intervals. Why not? But it should be a high confidence level. Okay, we're going to assume, and this is a big assumption, that the population standard deviation sigma is known. Again, this might seem unrealistic to you, but we're going to assume this for now. And we're going to assume, here's another big assumption, the central limit theorem, the CLT for means, applies. We're going to need this. And when does the central limit theorem apply? When one or both of the following is true. If the Big Daddy distribution is presumed to be approximately normal. Remember, we dealt with examples before with IQ scores, where we assumed that the overall distribution was about normal. Then the CLT kicked in immediately. It didn't matter how big your sample size was in terms of our ability to apply the CLT. We can apply the CLT regardless of sample size, in principle, if the original Big Daddy distribution is about normal. But if the Big Daddy distribution is perhaps unknown, or we cannot presume it's normal, maybe we're talking about dice. The distribution for one die result is uniform, discrete uniform. Remember that? That wasn't normal. So if you don't start with a normal distribution, right, then you're going to have to rely on having a large sample size. The convention is the sample size would have to be greater than 30 if we're not allowed to assume approximate normality in the Big Daddy distribution. The 30 does not come from algebra, it just comes from practical observation. But in order for the CLT to apply, we either have to start with a Big Daddy distribution that's about normal, or in the absence of that, or if you're not sure what distribution you're starting with, then you'll need to rely on a large sample size in order for us to be allowed to apply the central limit theorem. So again, in this section, we're trying to find confidence intervals for a population mean, where the population standard deviation is presumed known, and the CLT applies. In a way, this is also kind of an assumption. It's our goal. We're estimating a population mean mu. Okay. What's our formula? It ultimately comes down to this. And you'll find this in many books, just written straight out. Our confidence interval for a population mean mu, again, remember, it's got to be centered at the sample mean, x bar. Okay. Remember our picture before for test scores, right? Here's our confidence interval, Igor's confidence interval for mu, the overall mean test score for the class, the population mean. When Igor graded 5 tests that were randomly sampled, he found that the sample mean was 74 points, and that has to be at the center. That has to be at the center of any confidence interval we form for the population mean mu. We require symmetry about the sample mean, 74 points, for a CI for mu. X bar has to be at the center. Give or take E, this margin of error, which is given by this formula over here. Now, of course, this formula here, if I were to just throw this at you, you might freak out. It might be easier to look at it this way. Again, our confidence interval for mu, the population mean, is centered at the sample mean, x bar. The mean, the population mean, we believe, is the sample mean, give or take this margin of error, E. I'll put this in blue. This margin of error, E, where E itself is given by this formula. And then when you put these pieces together, then you get this formula on the bottom. A confidence interval for the population mean mu is given by the sample mean, x bar, which is at the center, give or take this margin of error, E, which is given by this formula. And why does this all make sense? Because, again, the CI for mu, a CI is my abbreviation for confidence interval. It's an acronym. The confidence interval for mu has to be symmetric about x bar, the sample mean. Remember this picture over here. We need symmetry about the sample mean here, the 74 points. And what's the deal with this formula for the margin of error? Well, take a look. We have this z-score. Notice that notation is the positive critical value. That z sub alpha over 2 is the positive CV, the positive critical value. So for example, so here, generically, it's over here, the positive critical value for the z distribution. If you want alpha total in the two tails. we split the alpha up into halves by symmetry. Okay, for a 95% confidence interval, anytime we want a 95% confidence interval where z is involved, we're going to want 1.96 as our positive critical value. And the plus or minus in this formula also automatically picks up the negative 1.96, the other critical value. Okay, so the margin of error consists of, all right, this positive critical value times this piece over here. I'll put this in purple. And where did that piece look familiar? Where did that piece look familiar? The sigma over root n. Where did that come from? The sigma over root n. That came from the CLT. That's why we had to make sure that the CLT even applied in the first place. Because, remember, this is the standard error for the mean, right? It's the standard error for the mean. The standard deviation of that X bar distribution we were talking about way back when. All right, sigma over root n. So it kind of makes sense then. Of course, the confidence interval is centered at the sample mean, X bar. And then for the margin of error, we have this positive critical value. That's how the confidence level influences the margin of error and therefore the confidence interval. The confidence level tells us what this positive z-score is. And remember, the larger the confidence level, the larger the positive critical value is. Remember, for a 95% confidence interval, the positive critical value for z was 1.96. For a 99% confidence interval down here, the positive critical value was all the way up to 2.58. So the larger the confidence level is, going from 95% to 99%, say, the larger this positive critical value is. So then the margin of error will be bigger. This half width here will be bigger. Because for a larger confidence level, we're going to end up with a wider confidence interval. And then this piece, sigma over root n, the standard error from the central limit theorem. All right, so how do we get the limits for the confidence interval? It makes sense. You start the sample mean in the center. You start the sample mean in the center, and then how far do you walk to get the lower limit and the upper limit of the confidence interval? You walk z, this positive critical value, z of these standard error pieces away. So you start the sample mean, X bar, and informally, you're walking z standard errors away, whereas the z-score here is the positive critical value. For a 95% confidence interval, you walk 1.96 standard errors away. For a 99% confidence interval, you walk 2.58 standard errors away to get the limits. If you didn't quite get that, we'll do a particular example in just a moment. By the way, before we do our example, a rounding rule. Because when you work out the margin of error, you're probably going to get a long, messed up decimal. What's the rounding rule for rounding off the margin of error? And this ends up leading you to round off the limits for the confidence interval. Like over here, the limits were 70 points and 78 points. The rounding rule for the margin of error, E. You round off the margin of error, E, to the same number of decimal places as the given value of the sample mean, X bar. So for example, if the sample mean is rounded off to 2 decimal places, you round off E, the margin of error, to 2 decimal places. And then the limits of the confidence interval will also be rounded off to 2 decimal places. If you want to be conservative, basically playing it safe, and often in statistics, we want to play it safe. We want to be conservative. That's not a political order, okay? It's a statistical piece of advice. When in doubt, be conservative. Play it safe. You don't want to be sued. And if you want to play it safe, round up the margin of error, which has the tendency to widen the confidence interval. Because remember, if Igor is saying, I'm 95% confident that this confidence interval contains mu, the actual population mean for the class. Well, if Igor wanted to be safe, okay, then Igor might want to extend this out. Okay, maybe it's better for him to say from 69 points to 79 points. So that the true population mean turns out to be 78.5 points or 69.5 points, then we won't sue Igor. I don't think we'll sue our TA, but hypothetically, we could sue our TA if the true population mean is not in the confidence interval. All right, so if Igor doesn't want to be sued, he might want to play it safe and move out the limits a bit. Play it safe. Raise the margin of error a bit and move out the confidence limits, the limits of the confidence interval a bit, within reason. Because I mean, if you were to go out to like 0 points to 100 points, yeah, that's a 100% confidence interval. That's not what we're aiming for. The idea is that we're asking Igor to give us a 95% confidence interval, so the confidence interval he gives us should have a confidence level of about 95%. It might actually be a bit higher in practice. Like if he tells us that the confidence interval is in fact from 69 points to 79 points, then maybe that's actually maybe a 96% confidence interval. Okay, close enough. But if you try to give a 100% confidence interval, you're making it too wide. Okay, but anyway, if you want to play it safe, round up the margin of error. I'm not going to make a big deal of this, but in statistics books, you're sometimes told to play it safe so that you're not sued, for example. And if you want to play it conservative, if you want to play it safe, you want to round up the margin of error. But if you round off, I'll be fine, as long as you do it to an appropriate number of decimal places, namely the number of decimal places that X bar is rounded off to. Wow, I just did a lot of talking. I'm going to refer back to all of this when we do our first example.
Okay, which will be now. So yeah, this sounded like, oh my gosh, what's going on? The example helped a lot. Questions before then? Okay, I think you want to see the example. Okay, questions. All right, let's do the example.
Next time.
Now.
Hi, everyone. By the way, after this video, you should be able to do the first 2 problems on lesson 28. So you can finish the homework up through lesson 28, homework problem number 2. Okay, so back to lesson 28, estimating a population mean mu in case sigma, the population standard deviation, is assumed known. Again, that might seem like a strange assumption, but let's start with that. And furthermore, we're going to assume that the central limit theorem applies. So make sure that the CLT applies if we're applying these methods, meaning that either the Big Daddy distribution is normal or the sample size is large enough, bigger than 30, say. All right. Now our formula for a 1 minus alpha confidence interval for mu, 1 minus alpha, it could be something like 0.95, 0.99, for example, all right? That's a confidence level. The formula for the confidence interval takes on this form. The population mean mu, we believe it can be the sample mean X bar, give or take the margin of error E. Again, we're using plus or minus differently from, say, the quadratic formula in algebra. The idea is that we believe that the population mean is within E units of the sample mean. Now, the margin of error is obtained by this formula, which is the positive critical value times the standard error of the X-bar distribution. So this all kind of makes sense. To get the limits of the confidence interval, which are obtained by taking the plus case and the minus case in this formula, to get the confidence limits, the limits of the confidence interval, you start at the sample mean and you walk Z standard errors away, where the Z score here is the positive critical value. The confidence level has a direct impact on what this positive critical value is. The margin of error, by the way, is always positive. All right. To be conservative, round up the margin of error and use the same number of decimal places as the given value for X bar, the sample mean. All right. Example 1. Let's apply these ideas. We're going to develop a 95% confidence interval, CI, for a population mean mu. And we're going to assume that the population standard deviation is known. So here's an example of where that could happen. Let's say a machine is designed to make cartons of 16.0 fluid ounces of ice cream. The amount of ice cream in the cartons is approximately normally distributed with population standard deviation 2.35 fluid ounces. And we're assuming this is the population standard dev, sigma. So this is going to be a kind of calibration problem. We're going to assume that the machine always exhibits the same amount of variability among the cartons of ice cream that it produces. However, we're wondering if the machine needs to be recalibrated in the sense that we're wondering if the machine might be producing too much ice cream to put in the cartons, or maybe it's putting too little ice cream in these cartons. These cartons are labeled 16.0 fluid ounces. So if they're going to be honest, if they're going to have that balance between satisfying the consumer on the one hand and making their profits legitimately on the other hand, they want to make sure these cartons are averaging pretty much 16.0 fluid ounces. Also, truth in advertising. They want the label to be accurate so they don't get either sued or maybe they'll get in trouble with the government. All right. Or the Better Business Bureau. Okay, so let's say the ice cream company wants to know, does this machine need to be recalibrated? Okay, are we concerned that the machine is putting too much ice cream, too little ice cream? We're assuming that the variation is the same, but we're wondering if the machine is putting too much or too little ice cream in the cartons on average. So the company hires some people, some statisticians, and they take a random sample of 19 cartons. The sample size, little n, is 19. We don't care about big N. Big N could be in the thousands or millions, but it's going to be way larger than little n. So we can assume independence and all that. The sample mean, let's say, for these 19 cartons is 17.2 fluid ounces. So you can imagine an Excel spreadsheet with 19 entries where they input how much ice cream is in each carton for these 19 cartons, and you can get the sample mean for these 19 cartons. How much ice cream is in these 19 cartons on average, and we get 17.2 fluid ounces. That's our value for X bar. I hope you know that. All right. Find a 95% confidence interval. 95% is our standard confidence level. For the population mean mu, right? The population mean amount of ice cream per carton. So we want a 95% confidence interval for mu, where mu is the population mean amount of ice cream per carton. Okay, so we're going to write the confidence interval, the CI, in two forms. One is in this form. I'll put this in blue. We're going to say that the confidence interval for mu is going to consist of the sample mean, give or take a margin of error, E. We're also going to write this confidence interval in the form lower limit, comma, upper limit inside parentheses, or even brackets. Once we get the confidence interval in this form, we can take the minus case and the plus case, and we can figure out the lower limit and the upper limit. So once we get this form over here and get the values here, then we can figure out the lower limit and the upper limit for the CI. Finally, let's interpret the confidence interval, the CI, using proper English. As a hint, or you could get this from software, like Excel, we're going to use the fact that 95% of the Z distribution will lie between these two critical values, negative 1.96 and positive 1.96. In other words, since we're going to use the Z distribution here, to get a 95% confidence interval, we're going to need these two critical values, which always correspond to a 95% confidence level when Z is involved. So let's do it. We're going to find the confidence interval, write it in these two forms, and interpret it. Let's do it. Okay. First off, just as a shorthand here, let mu be all of this, the population mean amount of ice cream per carton. Ideally, you would write that out. And why do the methods of this lesson apply? What assumptions are holding? Well, we're finding a CI for mu and not p or sigma or something else. We're finding a confidence interval for a population mean mu. We're assuming that the population standard deviation sigma is known. We're assuming sigma is known, 2.35 fluid ounces, because the company is taking that for granted. They think that the population mean might be different from 60.0 fluid ounces. Maybe that changes over time potentially, but they're assuming that sigma stays the same. It's a calibration problem. We're assuming also that the ice cream amounts per carton are approximately normally distributed. Okay, we assumed a normal distribution for the Big Daddy distribution. Therefore, what theorem applies? The central limit theorem for means. Okay. Our cast of characters, our sample size, little n, is 19 cartons. The sample mean, x bar, the average amount of ice cream per carton among the 19 cartons was x bar, 17.2 fluid ounces. Maybe you get that from your Excel spreadsheet. We assumed that the population standard dev, sigma, was 2.35 fluid ounces. That was given in the problem. So let's find the margin of error. Okay, so that's where these formulas come in. That's where these formulas come in. And I'll give these formulas on an exam. Okay, here's the formula for the margin of error. It's this positive critical value times the standard error, sigma over root n, from the CLT. All right. Again, the critical values are going to come from our hint. 1.96 is our positive critical value, z sub alpha over 2, or half alpha. All right. The margin of error is given by the positive critical value, 1.96, for a 95% confidence interval. Again, for a 99% confidence interval, as we'll see, this will be bigger. It's going to be 2.58. And then the standard error, it's sigma over root n, 2.35 over the square root of 19. Work this all out. Be careful, but work this all out. If we round off to 1 decimal place, we get 1.1 fluid ounces. Now, 2 comments. First of all, we're rounding off to 1 decimal place because the sample mean, it appears, was also rounded off to 1 decimal place. Now, if you wanted to be conservative, then you would actually round up. I forgot what you get when you round up. It could be 1.1 or 1.2, but bear in mind that you could round up. So if the margin of error on your calculator turns out to be 1.13, let's say, by the argument of being conservative to play it safe, you could round up 1.13 up to 1.2, and I'd accept that. You're being conservative in that case. Anyway, we're going to say the margin of error is 1.1 fluid ounces. So our 95% confidence interval for mu, the population mean amount of ice cream in each carton, if you consider all the cartons produced by this machine, at least nowadays, okay, is given by this. The confidence interval for mu is given by the sample mean x bar, give or take e, the margin of error. X bar is 17.2. The margin of error is 1.1. Notice they have the same unit. It's fluid ounces for both the sample mean and the margin of error. Okay, and we've answered part of the problem. Okay. We have found our 95% confidence interval in this form here. Mu equals x bar plus or minus e. We found the form and we found the appropriate values for x bar and e. And then, just by taking the 2 cases and separating them, you can find the lower limit and the upper limit. Remember, the lower limit corresponds to the minus case. Be careful. Okay, it's always going to correspond to the minus case. 17.2 minus 1.1. That's going to be about 16.1 fluid ounces. The upper limit, that's when you take the plus case. Okay, 17.2 plus 1.1. Whoops, that should be a plus sign there. Plus 1.1, and that's about 18.3 fluid ounces. So our 95% confidence interval for mu in this form, where we indicate the limits, is from 16.1 fluid ounces to 18.3 fluid ounces. Technically, you should put units. And remember, the lower limit is obtained from the minus case here. The upper limit is obtained from the plus case here. If for some reason you find it easier to work out the upper limit first, that's fine, but make sure to put the upper limit to the right. Interpretation. We are 95% confident that this interval contains mu, the population mean amount of ice cream per carton. But you don't want to write mu in your statement for the layperson. You want to write out what mu means. So as a practical matter, what's some good business advice for the business? Wait, these cartons were labeled 16.0 fluid ounces. What's happening? What is actually happening? Based on our sample results, what does it look like is actually happening? It looks like too much ice cream is going into these cartons. Okay. In fact, notice here, this interval does not contain 16.0 fluid ounces. So if anything, we're very sure that the 16.0 fluid ounces is out of whack. We're pretty confident. We're very, very confident, in fact, that this machine is putting too much ice cream in the cartons on average. So what should the ice cream company do as a practical strategy? Well, the cartons are supposed to contain 16.0 fluid ounces of ice cream, yet the 95% confidence interval here, that's a pretty high confidence level, that's a very high confidence level, does not contain 16.0 fluid ounces. So based on this analysis, the ice cream company has sufficient evidence against the claim that the population mean is actually 16.0 fluid ounces. In the last part of this course, we're going to use a lot of this kind of wording when we do hypothesis tests. The ice cream company has sufficient evidence against the claim that the population mean is 16.0 fluid ounces. It's putting in too much, looks like. So it may want to recalibrate the machine so that it puts less ice cream in the cartons. So the danger for the company is that the company might be wasting ice cream. It might be wasting money in a way because it's putting in too much ice cream into the cartons. They may not get in trouble by the government or from consumer groups, maybe from dieting groups, Weight Watchers, but internally, they may be wasting money because they're putting too much ice cream in the cartons. Next up, what if instead of a 95% confidence interval, we do a 99% confidence interval? And think about it. How will this be different?
So I wanted to really introduce these ideas, and in fact, you could do lesson 28 if you follow this, but I'll be continuing with this next time. So basically, I want to give you a great solid introduction to lesson 28. This may be enough, actually, to even do 28, all right? Next week we'll be busy. Okay, I'll be continuing work on the homeworks as well for my classes. All right, so we have, okay, I might play the videos during the homework session. I sent those out anyway. All right, so it's 9:33, all right. Okay, so it was just a matter of playing these videos today, but I will stick around for any questions you have, either about the concepts or maybe you've been working on the homework so far, all right? Check out those cute little video links. I may play them in class during the homework session. What was it? It was a game show. They're both game shows. Yeah, 2 game show videos. All right, so for some of you, good night. Otherwise, I'll stick around for questions. I'll continue with lesson 28 next time. All right. Click this off. All right, any questions? Any questions? Okay, you're welcome. Have a good night. Get cracking on the homework. Otherwise, if you don't have questions right now, I'll come back in 3 minutes at 9:38 when my computer says 9:38. So 9:38, I will be back. In the meantime, I'm going to mute and I'll pause the recording. So I'll record when I get back. All right. So for now, I'll mute and record. Mute and pause recording. I'll come back at 9:38. See if you have any questions. All right. Otherwise, have a good night.